All right, last we left off, we were introducing the pumping lemma for context-free languages. And we talked about needing to pump the string in two places rather than one. And the reasoning for this was that there was something circular about the grammar, where we could go from a non-terminal back to that non-terminal through some sequence of productions. And that process was a loop. It could then generate an infinite number of strings in a language by iterating through that loop an arbitrary number of times. So we said, let L be an infinite context-free language. There exists some positive integer m such that any string w in the language with the length of w greater than or equal to m can be decomposed into 5 parts, u, v, x, y, z, with the following constraints. The length of vxy, so the length of the pumped 2 portions, plus any constants that get revealed in the middle of those 2 pumped strings, that's the x. The length of that entire substring has to be less than or equal to m. And the length of vy, that is the length of the combined pump, needs to be greater than or equal to 1. So that means that either v can be length 0 or y can be length 0, but not both. So from the start non-terminal, we're able to produce some non-terminal A that's going to be our looping non-terminal, the thing that we come back to. However it is that we get from S to A, we're going to produce on the left side some terminals that we'll call a substring U, and on the right side we'll have some terminals that we'll call the substring Z, and that's just the terminals that we generate as we move from S to A. Because there's no guarantee that S is immediately defined in terms of A. S could be defined in terms of S sub 0, which is defined in terms of S sub 1, which is defined in terms of S sub 2, which is defined in terms of B, which is defined in terms of C, which is defined in terms of A. So whatever it takes us to get to that A, any terminals that we produce on the left-hand side or the right-hand side are going to be what we call U and Z. Then there's the process of getting from that non-terminal A back to that non-terminal A through some loop. It may be that we define A directly in terms of itself. Maybe we go through a big long process of A goes to B, goes to C, goes to D, goes to E, goes back to A. And whatever is produced as we do this on the left and right-hand side of our string, we're going to call V and Y, because the loop of going from the non-terminal A back to the non-terminal A can continue to produce V and Y an arbitrary number of times as we do that loop in the grammar. Finally, we're going to decide to terminate. And to terminate, we need to turn the non-terminal A into some number of terminal symbols in the middle of the string. So whatever that process looks like of converting the non-terminal A into some terminal representation where we have a full string with no non-terminals, that's what produces X. So just like before, where we needed an intuitive idea of what each of these symbols are, that's also true here. We really want to know what UVXYZ stands for and what each of those mean if we're going to have any hope of being able to generate intelligent strings for pumping lemma proofs. We need to be able to break down this problem and understand it at a deep level. So once we have this, we have the breakdown UV to the I, X, Y to the I, Z, and that will produce a string in the language for any I, 0, 1, 2, etc., any of the positive integers and 0. We know there are a finite number of productions in the grammar and an infinite number of strings in the language, so the pigeonhole principle still applies, just like it did before. So that means that there exist derivation trees of arbitrary length. So one other way that you could think of visualizing what's happening here is with a parse tree visualization. And we talked a bit about parse trees before. Who can recall what a parse tree is? Back, maybe?
Yeah,
Yeah,
it's like, I don't know if I'm gonna use the right words for it, but it has to do with the different productions that will get you to a specific point in the string or get you a specific string.
yeah, so we're gonna start with basically the the start non-terminal. And we're gonna start breaking that down. Whenever there's a choice of which production we might apply, we have to choose which production we're applying. And that helps break down that into more and more and more symbols, and eventually we can do a depth first search through the parse tree to be able to reconstruct what the string is that we've generated. Yeah, exactly. So here's how we can visualize it. So we go from the start non-terminal to this non-terminal A. And as we do so, we're building the string kind of from the outsides in. So through that process, we will have defined U and Z. By the time we reach A for the first time, U and Z are finalized. Then we're going to loop from A back to A, and whatever we do through that is going to define B and Y. We can do that an arbitrary number of times, producing an arbitrary number of B's and Y's, but eventually going from A to a terminal representation, then we generate X. And that's what's needed for this to be context free. If we're doing this with a stack, right, we can only build from the outsides in, not from the insides out. We have to generate some stuff, push it to the outside, generate some stuff, push it to the outside. And that's just the nature and the downsides of using a stack. So these are all the languages we can represent through generating in the middle and pushing toward the outside. Questions on either of these visualizations or representations of how we're going to phrase pumping lemmas for context-free languages? All right. So let's tie this back to the pumping lemma game. This is one thing that I've seen throughout talking to people, and it's worth taking a brief aside to talk about the difference between the pumping lemma game and a pumping lemma proof, because they're not quite the same thing. The way that I wanted to talk about this is, let's go back to talking about the pumping lemma in the regular language form, just for a second. So M in this case represented the number of states of a DFA that one could construct. If we're going to make a game out of this, then it starts with player one saying, I can make a DFA with size whatever, be that 3 or 5 or 8. And so the pumping lemma game has you selecting. I don't know if we'd ever really had a language that has a DFA of size 0. I don't think so, so we can probably get rid of 0 here. But you can imagine now that this continues. And what the pumping lemma game is going to do is basically player one is deciding which one of these numbers is correct, saying I can produce a DFA with exactly 8 states. If you go through the pumping lemma game at this point and show that they're wrong, then what you have shown is that a DFA of size 8 does not exist. And is this a whole proof? If no DFA of size 8 exists, could there be a DFA of size 9 that exists? Yes. A DFA of size 12? Yes. A DFA of size, it doesn't matter, as long as it's not 8. It kind of eliminates those that are less than it. You can come up with a useless DFA with some unreachable states of size 8, where some of them solve the problem, but it doesn't say anything about those that are greater than it. So we need to have some kind of generic proof that says, no matter what you pick here, I have a process where I will win the pumping lemma game. So this is why if you're going to write out a pumping lemma proof, it needs to be in terms of the variable M, and not a particular instantiation of M. So you cannot make a pumping lemma proof for size 5, but it's a great way to visualize the problem. So if we were trying to show the pumping lemma for A to the N, B to the M, right, I guess A to the N, B to the N. Easiest example we can find. We said the string we wanted to choose is A to the M, B to the M, because that's its generic form. But it's easy to visualize and start playing around with what needs to be done if you choose a particular value, like 3. That means the string is A, B, and not A to the M, B to the M, which is more abstract, more difficult to work with. On the other hand, now we have 3 A's and 3 B's, so we can actually visualize and say, well, if M equals 3, we can highlight the first 3 characters, and we can see a bit more visually how repeating any of those characters will lead to strings that are not in the language as we pump that. Does that make sense as to why we need our pumping lemma proofs to be in terms of M, anything that they could choose? Because that language, even though the argument is exactly the same, if we were to compare the arguments for just M equals 3 to just carrying through M, nothing actually changes about the proof structure. It's just that you're carrying M all the way through, saying that no matter what is picked, I can phrase responses based on that particular size. So that takes this problem and turns it into this problem where you're solving it for all possible values of M because you've carried M all the way through the proof. Yeah,
You wanna, just so that people can see it, like. Show what the final one kind of looks like, because it would be like A to the M plus the absolute value of Y.
yeah.
Is that?
So- If we're gonna prove this, we would want to say, all right, the string we're gonna choose, regardless of what player 1 chooses, is A to the M, B to the M. And so the string is some number of A's, some number of B's, that some number is M. We need to have an abstract argument now. So based on this, we come back and player 1 is going to give us the breakdown of X, Y, Z. So given that we're going to have some options here. And again, I'm pointing back to the M equals 3 because it's easier to see with a concrete example. But this could be X, this could be Y, this could be Z. We could have X as 2 A's, Y as a single A. Or we could have a Y that is the whole thing, have no X, have a Y that is the first 3 A's, and a Z that is the last 3 B's. So we have some number of choices, or player 1 has some number of choices as to the breakdown of X and Y, following the constraints that the length of XY has to be less than or equal to M, and the size of Y has to be greater than or equal to 1, which is why we can't have a Y of size 0. But in all of these cases, regardless of what M happens to be, Y must be all A's, which is the important part of the proof. Y has to be all A's, no matter what the size of M is and what the breakdown of XY is, that player 1 gets the choice for. So because of this, we know that the number of A's that we're adding, if we choose something like I equals 2, is the length of Y. So if we wanted to represent this, you would say that after or for I equals 2, the result would be A to the M plus the size of Y, B to the M. Right? If we're going to say we're going to repeat this loop one more time, the extra number of A's that we're adding is equal to the length of Y, if we pump that one more time. So generically, we can show this by A to the M plus length Y, B to the M. And since one thing that we had in our prerequisite rules was that we knew the length of Y has to be greater than or equal to 1, you use that argument right here to show that we don't have the same number of A's and B's. Length of Y cannot be 0, so this cannot be equal. The number of A's and B's cannot be equal. We have to have more A's than B's after the pump, no matter what was chosen for M. The value of Y has to be all A's and at least 1. So this will hold, and you can use this as the final proof as you tie it together. That's the contradiction. We've produced a string that is not in the language. And this is a way to produce a string that's not in the language, regardless of what player 1 does. Regardless of what M they choose, and regardless of what breakdown of X, Y, Z they choose, it always has to follow that there are more A's than B's in the final string when I equals 2. And remember that we only have to come up with an example of a string that's not in the language, which is why we can pick a particular I here. And in fact, frequently we pick either I equals 2 or I equals 0. If you picked I equals 0 here, we'd have M minus the length of Y, which would also work. So stuff like that. Questions on this example, questions on the proof format, how to relay your answers? Okay, so what changes with regards to the pumping lemon game when we're talking about context-free lengths? Just like before. Player 1 picks M. Player 2 picks a string in the language that is length at least M. Now is where we get to the slight changes. Player 1 will choose the decomposition of VXY, not XY. Now it is VXY. And their choice must adhere to the constraint that that total length is less than or equal to M. If that constraint didn't exist, this entire thing would fall apart. That constraint is highly important here. Player 2 then chooses a value of I, such that, however they broke it down, their VXY, UV to the I, XY to the IZ is not in the language. So again, extremely similar. The problem. Give me just a second. It looks like because of my computer's blue screen that animations starting at this slide have failed. So I will at least, oh no, it's just a single slide. Oh, that's weird. All right. Easy enough to fix. Okay. Starting to get into some examples. We'll start with the language A to the N, B to the N, C to the N. So we know A to the N, B to the N is context-free. But I am asserting that A to the N, B to the N, C to the N is not context-free. So starting here, what do we think a good string to pick is? Let's take just a second and let people think about this. What do we think is going to be a reasonable string to be able to show this?
I don't know, to the third.
So when we had A to the N, B to the N before, what string did we pick to be able to show that? We picked A to the M, B to the M for whatever M happened to be.
Yeah, so okay.
So if we pick A to the M, B to the M, C to the M, if the goal is to show something like if we pump V and Y for some VXY, where the length of VXY has to be less than or equal to M, what does that constrain us to do? It no longer has to be within the first M characters of the string. It can be anywhere in the string. We're going to end up with something like 5 cases where player 1 now has the ability to pick all A's as the breakdown, all B's as the breakdown, all C's as the breakdown, some A's and B's as the breakdown, or some B's and C's as the breakdown. Because they have to appear within M characters of each other. So we can't get A's and B's and C's. But they could pick a sequence of M characters that's either all in one or it's between 2 that are adjacent to each other. There's no way that we can produce all three. So given that, how should we proceed? Any ideas? Yeah,
So is it wrong to be like? Choose A and C as far as like the trying to think it's U, V, X. W, Y. Anyway, for the B to be like some sort of A's, and then for the C to be some sort of Y. The Y's that we use, or it's the yeah. But the things that we pump essentially is the A and C's.
yeah, the B's and the Y's.
Yeah.
There's no such way to pump A's and C's.
Okay.
The reason is that there are M B's, and we know that the entirety between the leftmost thing that gets pumped and the rightmost thing that gets pumped has to be at most M characters. So there's no way to be with one side of them on the A's and one side on the C's, because there are M characters, M B's in between them. So we could either pick something that's all A's, all B's, all C's, or we could spread the M amongst A's and B's. So starting in the right part of the A's and ending in the left part of the B's, or starting in the right part of the M, the B's, and ending in the left part of the C's.
So and B, I guess.
So we have 5 cases to deal with. We need to be able to show that regardless of any of those 5 cases, we end up with some particular I of a string that's not in the language. So we kind of have to break down into A's, B's, C's, A's and B's, and B's and C's. Intuitively, before we even start with the proof, what's the issue with picking all A's? If player 1 picks, all right, there's a breakdown of VXY, so that means U is all A's, VXY are all A's. And then Z is all B's and C's, and possibly some A's too. But we'll just call this B's and C's for now. If we pump all A's, what is the final string that we get if I equals 2?
A to the M plus BXY.
Yeah. We get A to the M plus the length of VXY. B to the M, C to the M. And we know that the length of Vy without X at all, we know that the length of Vy is greater than or equal to 1. So we know, just like that proof format from moments ago, that there are more A's than B's and C's because of this rule. So I equals 2 will be a good pick here. I equals 0 would turn this plus into a minus. That would be great too. So that's going to check off this case. There are more A's than B's and C's, so it will not be in the language A to the N, B to the N, C to the N for some N. Because there are more A's than B's and C's. How about the all B's case? Question?
Yeah, so. I'm sorry, I'm a little bit confused with, if we're doing a proof, do we not pick a number?
We do not pick it.
For an example string, like I equals 2?
You can do that to help your argument or help your intuition, but the actual proof itself needs to work for any possible M, not just one particular M.
So like the example number I equals 2 would not be required for a proof, it's really just to help understand what an example string would look like.
You need the I equals 2, but you need to carry the M all the way through this proof. You cannot say something like, if M equals 3, then we end up with the string A, and then you carry through this exact same thing where you set I equal to 2 and you end up with either A, B, or A, B, C, because that will only work for a particular value of M.
But
To
like,
complete the proof, we need any value of M.
But on our homework, so we have to pick a value of I, but also a general value of M.
Yeah. Yeah, you pick a singular value of I, because basically for all M, you need to pick a single value of I that creates a counterexample.
Oh,
Does that make sense? We need to show for any value of M that for some value of I, it breaks. And you do not always have to pick the same value of I if you're breaking this into cases. You can pick I equals 2 here, I equals 0 here, I equals 3 here, I equals 12 here. Doesn't matter what I you pick, as long as there exists an I that breaks the case.
Are we choosing I? So that we can, because we're trying to like branch together concepts here, so like, are we choosing I so that we, because like normally you need to show in any example that you provide. When we're starting with some sort of string that we're choosing, we need to show that something is within the language before we break the thing, so like. Is that the reason why we're essentially picking I, saying I is equal to 2? In some, well, no, that's not true, because then.
Yeah, it's the number of times we go through that looping process.
Right.
Because if we start with something in the language and we pick a valid VXY, if this were to be context free, then regardless of the number of times we repeat V and Y, it should be in the language. So I is just telling us the number of times to go through that loop to generate something that's not in the language. Because to be in the language, every value of I would need to work.
Right.
So this provides the counterexample. This provides the proof for any number of M's, any number of, any size of the appropriate. Like, for instance, this is basically saying. If we were to, how do I want to say it? It's not as clean as it is in regular languages, where it's the size of the DFA. It's the size of the terminals that are being produced in between S and the first repetition of A in the prior example. So I don't know if I really want to go there, but it's basically the size of the structure. You want to say for any size of the grammar structure that this holds. Maybe that's the easier way to kind of generically put it. But we don't want it to be for a particular size grammar, particular difficulty grammar. We want to be able to say for any grammar that you could produce that would represent this language, there will be an example that gives you something that's not in the language.
And then, I know in the equation we wrote there for A, the BXY would just be basically multiplied by I minus 1, correct?
Yeah.
Okay.
Yeah, so if you chose a value that wasn't I equals 2, then you would have some slight change to this part of the formula.
And then I is the same for both B and Y, correct?
Yeah,
They would be
yeah, it does need to be the same for both B and Y. We don't have two different variables, it is X, sorry, not X, U, B to the I, X, Y to the I, it's the same variable, so it absolutely needs to have the same value. Questions on this example? You can do basically the same thing for B and C. If they're picking a VXY that's only B's, you're gonna end up with A to the M, B to the M plus the size of VX on X, Y, B, C to the M. And for C, you'd get A to the M, B to the M, C to the M plus the length of VXY. And in all cases, those are not going to be the same. So very similar logic will disprove cases A, B, and C. So all that's left is the AB and the BC. And what's nice about this is if you add something to A and something to B, it will not be the same as C. C is going to remain unchanged. We know the length of VXY has to be at least 1, which means we are pumping at least one A or at least one B. Regardless of where you pump those things, you pump just A's or just B's or A's and B's, you end up with more A's or B's than you have C's.
Notation wise, is it gonna be like A to the M plus the value or the size of B? And then X, and then you do B, M to the size of Y, then C to the M. Is that what that looks like?
It can be, yeah. The question though is now we have the ability for either B or Y to be part B's and part C's. So you can either use or part A's and part B's, it could be right on the border. So let's say for example's sake, we have A, B, C, and we pick X to be this, not X, here we have U, V, X is empty. Y is empty, and Z is the rest of this. So the pump here is AB, 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 AB. So one, it breaks the A to the M, B to the M, C to the M format. And two, you still end up with more A's and B's than C's. So you can make some argument, but you don't know exactly how many, and it's going to be difficult to come up with a formula for exactly how many A's and B's were added. So you probably need some kind of logical argument rather than just representing it as an expression. Some logical argument that says no matter where B and Y end up, we know they're in the A's and B's. So because those get pumped and because something has to get pumped, the length of Vy has to be greater than or equal to 1, then we end up with either more A's or more B's or both than C's. Therefore, it's not in the language. Does that make sense? No matter what the breakdown is, you end up with something that's not in the language. We know that Vxy have to come somewhere in this part of the string. Regardless of whether it's all in the A's, all in the B's, which are covered by these cases, or there's something in the Vxy that is between the A's and B's. The B could be in the A's, the Y could be in the B's.
So what you're saying makes general sense. I get that it can be, V can be the AB, it could just be the A section with some way that X is not kind of there with Y being some B's, or Y could be, V could not be there, it could be X is like nothing, and then Y could be AB's. I get that. I don't know what that looks like notation wise to provide some sort of like.
Yeah, it's gonna be really tough to come up with exact set notation for that. So my logical argument would be something like we'll break this down into cases again, where we have B is all A's, Y is all B's. Then you end up with something that says there are more A's and B's than C's because of how this is set up. We could say B is A's and B's. Y is 0, length of Y is 0. So then we again end up with more A's and B's than C's. Logically follows. And we could also have length of B is 0. Y is A's and B's. If that's the case, then we end up with more A's and B's than C's. So no matter how you break this down into any of the associated cases, this holds when I equals 2. And then you do the same thing for the B's and C's. And it turns out that context-free pumping lemma proofs are a lot more involved, even in their most base case, than regular language proofs. Because you often find that you end up with lots of cases, and then you have to break those cases down into their individual proofs. And then you have to show that for any possible breakdown, so all cases have to end in a contradiction. So again, it's the same style, it's just much more complicated. How are we doing? Does this outline make at least logical sense? Even if there may be some notation questions in there, we can always generate those with some practice examples.
You have to write it out for each case.
You will need to write it out for each case, yeah, just
Okay.
because if there's a single counterexample to a particular case, player one can still win the game by generating a particular breakdown of VXY that says, hey, I found the grammar type that allows us to represent this in a context-free form. Just because you couldn't for some other forms doesn't mean that there exists a form of the grammar that would work. So basically, these are all the different forms of the grammars that you could produce, different places that you could expand and repeat. And if there is a way to continue to produce an infinite number of strings that are in the language, then it is context-free by producing a grammar that follows that particular kind of form.
Were we supposed to do that with the last pumping lemma too?
There weren't too many by cases in that one because you're only pumping a single thing. So yes, if it could have come from a bunch of different cases, if it was something like, can't even come up with an example off the top of my head. I'm not sure there was one. Because we had the additional restriction that the length of XY had to come within the first M characters. So if you had an intelligent string, like for A to the N, B to the N, A to the M, B to the M, you could only fit them into the A's. So there was only one case to show, pump all the A's. But because we relaxed that restriction here, and VXY can come anywhere in the string, we end up much more frequently breaking it down into cases because we can't create an example that eliminates all of those cases.
These will take a long time.
These will take longer. There will be fewer of them on associated homeworks. If there's something on an exam, it will be a very simple example, so you don't need to draw out 20 cases and try to prove them all in 50 minutes. I am aware of how time limited we are, and I want to test more than one thing. I'm not going to hand you an exam with a single pumping lemma proof on it and say, yeah, there are 20 cases, but it's the only question on the exam, go. So if this appears on an exam, it will be in a very simple form with as few cases as I can find so that you can finish. All right, let's see how some of these other cases look. So player one can pick VXY, only A's, mix of A and B's, only B's, mix of B and C's, or only C's. So I have a much simpler form here in just words. I wanted to go through and show you what the actual proof would look like. But the conclusion of going through all of that work is regardless of the breakdown, any I greater than 1. Anytime we pump the V and the Y more than once, we produce some string that's not in the language. And because for every one of those examples, there's a counterexample, then the language is not context-free. But you do have to go through all of those cases, which is laborious. Ready for the next example? I think I have 4 of them because there are so many, there's a lot that we should talk about. So here's a new language, WW. We want to show that a string followed by that exact same string is not context-free. First of all, what's the intuition for why this language is not context-free? Can we think of some intuition as to why that is?
Is it kind of like the last problem where the kind of thing?
Kind of, yeah. So we know that WWR is context-free, right? A string followed by that same string in reverse. But why would that string followed by that string not be context-free? What's the difference between a string followed by the string in reverse and the string followed by the string itself?
Reverse like, at least with stack, you can just go back down.
Yeah, it's because of the LIFO structure of a stack. If we could use a queue for this, if we had a context-free queue-like structure, then we could recognize WW and not WWR. So thinking about that intuitively like this, using a stack, there's no way to access the bottom of the stack non-deterministically to figure out, all right, maybe we can lambda transition and start reading from the bottom of the stack, but we can't do that. So that's where our language is going to fall apart. So let's start thinking, what is a good string to pick for WW? Now we have some options.
So.
First thought was just like A to the M, B to the M, A to the M, B to the M,
Why?
because any segment that you do will only affect one half of it. So any other half will be, like, you can pump away from it.
Yeah.
Essentially.
We're still gonna end up with some cases here though, right?
Yeah.
The VXY could appear where?
All A's, A and B, all B's, B and A, all A's again, A and B, or all B's.
Yes. So luckily, a couple of those are mirrored cases, like if you
Yeah.
pick all A's and all A's on the first part or the third part, you can combine those into a single argument. If you pick A's and B's in the first part or A's and B's in the last part, you can combine those arguments. B's from the second part and B's from the fourth part, you can combine those. But we again have to break down into those cases and solve them all. It's tempting to think you can get around it by saying, what if we chose A to the 2M, B to the 2M, A to the 2M, but you'd still have exactly those same cases? There's no way to get around. You could pick somewhere right in between those, no matter how long you make that. So we don't save anything by choosing longer strings. So we have 4 cases. All right, if we're doing the A's followed by B's case, this is where it gets a little bit hairy, because we have some cases here. Either V is pumping more A's than Y is B's, which means that V has some A's and some B's. So either there are more A's being pumped than B's, more B's being pumped than A's, or the more difficult case, what if there are the same number of A's and B's that are getting pumped? Because we need a different form of the argument if they're the same number. This is why we use the I equals 0. Because if there are the same number of A's and B's that get pumped here, what is the argument that we can make? What's a reasonable argument? We'd end up with something that looks like, this is not a complete argument, but I think it's easier to see this way. We have like A to the M plus length of B. B to the M plus length of Y. A to the M, B to the M. Is this still in the language WW? No. We need to now, rather than looking at the number of A's and B's across these, we need to look at, is this the same as this? Since the length of Vy has to be greater than or equal to 1, there's some change to this string and no change to this string. Likewise, if the A's and B's come from the right-hand side rather than the left-hand side, you just swap the order here, where we have A to the M, B to the M, A to the M plus length of B, B to the M plus length of Y, which again is not WW. It's not the same string repeated by the same string. So this breaks that case. And I shouldn't say plus here, I should say minus, if we're using I equals 0. Since that's what my slide is going to say, I'm going to choose minus here. Plus would also work. You can choose I equals 2, you can choose I equals any value, really, that's not 1. And the proof will follow. It's just a matter of, do you set it up in a way that works? But we don't have the same string followed by itself. We are way over time. Oh my goodness. But I'm too excited. So we'll come back to these for example tomorrow. Take a look at the study guide. Let me know if you have any questions about it, and I will see what I can do to get your homeworks back so that you can start studying those.
There was one thing I was gonna say.